Make easier the reading of properties of transition metals, they are divided into three groups. The early transition metal from S2D1 to S2D3 or from D3 to D5, the middle transition metals D6 and D7, and the late transition metals from D8 to D10 S1. In some books, especially the English books, they divided only the periodic table of the transition metals into two families, the early transition metals from D3 to D6 and the late transition metals from D7 to D10 S1. The early transition metals have low electronegativities with respect to the late, and they have higher oxidation state. The late transition metals have higher electronegativities and lower oxidation states. The low oxidation state metal tend to add soft ligands as Br-, I-, triphenylphosphine, ethene, C2H4, because these metals have excess of electron density. So they avoid strong donor ligands. They prefer ligands having empty orbital to retro donation of their excess electron density. The high oxidation state, as we said, from D3 to D6, the early transition metals have short electron density and tends to have good donor ligands. We have the column 12 starting by the zinc, but this column could not be considered as a transition metal. Zinc, for example, is not considered a transition metal because its compounds or ions like zinc 2 or zinc 2 plus contain a full d orbital, so it cannot receive electrons in d orbital. The zinc has S2 D10, zinc 2 plus has D10, so the orbital d is filled. It cannot receive electrons. But we will see in the next chapters that, for example, silver Ag in some cases has orbitals completely filled and it forms complexes. So we will explain it in the corresponding chapter. I will explain a typical formation of a bond Ml. The metal M has the orbitals dxy, dxz, dyz, dx2 minus y2, and dz2. And as you know, that these orbitals are in all directions x, y, z. So M practically has, by theory, d orbitals in all directions. That means it can receive the electrons from the ligand easily because it has d orbitals in all directions. The ligand L is three types. We have ligands which are sigma donor, like for example p-phenyl 3 and H3. We have lone pair on N, lone pair that can be donated to a metal along the axis, so the bond is on the axis. We call sigma donor. We have ligands which are sigma and pi donor, like carbene and carbide, and will be explained in independent chapter. And we have ligands that are pi donor, like for example cyclobutadiene or cyclopentadienyl. The bond Ml takes place when electrons from L are donating to M. The ligand L has a site donor, so it's sigma donor. For some ligands, we have vacant sites that can receive electrons, so is acceptor. The acceptance may be from the metal, and this is called the retro donation, and a metal can retrodonate to a ligand L if M is rich in electrons and not or, and if L has orbital acceptor. Most ligands form Ml bond by using a lone pair. So this is sigma Ml. Consider C2H4. If we draw to know the site of donation, we have to draw C2H4. The type of hybridization of each carbon atom is sp2. So we have C 3sp2 and the second carbon we have 3sp2 that form a trigonal planar geometry, and we have a pi bond between p orbitals. This is the structure of C2H4. So in red is pi, in green and in red is sp2, pi of p orbitals. From this side, we have one hydrogen, one hydrogen, one hydrogen, and one hydrogen. If we look to the structure of C2H4, we don't have a lone pair. We have a pi bond. So the donation of C2H4 to a metal M is from the p orbitals forming the pi bond to M. If the donation of these orbitals to the metal M is on the axis, this is a donation from p orbitals of C2H4 to M by a sigma bond. And if the donation of C2H4 to the metal M is from p orbitals of C2H4 by overlapping with the orbital d of the metal M, so the type of bond between Ml and L is pi. So pay attention, the donation is from the pi bond of C2H4, but this donation from C2H4 to M depends on the nature of the orbital M. If the donation is along the axis, so the bond Ml is sigma bond. And if the donation along the d orbitals overlapping, so the bond is pi bond. I will draw two examples of the donation of C2H4 to the metal M. The metal M has orbitals in all directions. This is a representation to say that the metal M has orbitals in all directions, and I will represent the metal M by this way. This is the metal M. Okay. If the bond, we agree that the bond is from the p orbitals of C2H4 okay, why this way? If the bond takes place with these orbitals in this direction, so this is sigma bond. Okay, so with orbital dashed by this way. This is donation of p orbitals of C2H4 to a metal M. We can have another figure where the donation is different. So the donation is between p orbitals of C2H4 by this way I will suppose that is with orbital for example. Okay, so this is a pi bond. If we look to these two figures, the donation is from p orbitals of C2H4, but the bond may be sigma or the bond may be pi, and we will explain this in details in the chapter concerning the metal-alkene bond. The aim of the organometallic course is to know if the organometallic complex can act as a catalyst or not, and to note that there are different number of ligands around the center metal. Too many ligands is bad because it will decrease the reactivity, and too few is also bad because it will decrease the electron density. For example, in this catalytic cycle, I will explain later, we have platinum complex, and this is the hydrosilylation. So the transformation of the double bond, the breaking of the double bond, and addition of hydrogen in one side and Si-methyl-3 in the other side. These two ligands in the mechanism are added to the catalyst used. So if we have too many catalysts, HSI-methyl-3 or alkene could not be added to the structure of the catalyst because the catalyst has too many ligands and we have steric effect. So this is not good. And I said too many is bad, I explain, and too few is bad. When we don't have ligands on the metal center, supposing, for example, the metal center is 14 electrons or 12. That means in the laboratory, you are working with solvents. You should add solvent to make this reaction. So any solvent added, for example, can act as a ligand because we have a vacant site on the metal, and this is not good. So the general conclusion, too many catalysts, too many ligands is bad because it prevents the addition of the reactant to the structure of the catalyst, and also too few is bad because the metal center is poor in electron and some reaction in the mechanism cannot take place with metal center poor in electrons, or the metal center is sensitive to the solvents used, so it can add this solvent and complicate the mechanism of the reaction. The first step to know if our catalyst can act, I say can act as a catalyst, is to calculate the electrons around the metal center or the electronic counting. If it's 18, so it cannot receive. This is not good. If it's 16, it can receive. So for 18 electron complexes, which are saturated complexes, in general, they cannot act as catalyst. They have to lose a ligand to become 16 electrons, which is unsaturated, then it can act as a catalyst. Chelate effect, we return to the fundamentals and notation. Chelate effect, or the term chelate, is from the Greek meaning claw, or to grab onto. The chelate effect, or chelation, is one of the most important ligand effects in transition metal coordination chemistry. As the chelation is strong, the chelation of L to M is strong, the bond Ml is more stable. And the ligands can be, for example, monodentate. That means it can bind to the metal M by one dentate, for example, a lone pair, and a ligand which is bidentate, it can bind to a metal M by two sides of this ligand, for example, ethylene diamine. En, ethylene diamine, we have two centers N that can bind to the metal M. So the polychelation increase the stability of the organometallic complex. This is a ligand monodentate. L is monodentate. It's bind to M by one dentate. So Ml can dissociate easily a ligand L to have Ml plus L. We will study this in details after. Supposing you have the ligand is bidentate, you have one chelation from L and other chelation from the second L. So in this case, M could leave one dentate to have MLL, but never the bidentate LL is released from M. When you have ethylene, when you have diphosphine ligand, when bound to a metal M, the metal M can release one atom P. So it becomes monodentate by the second atom of phosphorus, but never M release all the ligand diphosphine. Since most of metal ligand bonds are relatively weak compared to CC bond, so ML bond can be broken easily, leading to the dissociation of the ligand from the metal. And remember that Ml release the ligand L for several reasons. One, if the bond Ml is weak, that means the ligand L is not a good donor to M. Or second factor, the ligand L can be strong donor, but it's a bulky group. When the ligand is bulky, the metal M prefer to release it easily to maintain the stability of the structure obtained. We pass to the term hapticity. Hapticity, hapto, haptox, or etax, indicates how many carbons of pi system were coordinating to a metal center. For example, in this structure, the M is bound to 5 carbon atoms of a pi system, so this is hapto 5 Cp bound to M, or this is eta 5 Cp. In this figure, M is bound to 3 carbon atoms of a pi system, so this is hapto 3 or eta 3. MLL 1, 2, 3 M is bound to 3 atoms of a pi system, so this is a hapto-3 allele. In this structure, M is bound to 1 carbon of the allele and not to 3, like this structure. So this is eta-1 allele. Before we use in organometallic the term eta X or hapto-X only to indicate the number of carbon atoms of pi system coordinating to metal center, but the nomenclature has been generalized to most in the organometallic field to include even non-carbon ligands. For example, if you have M bound to a bidentate ligand, you can write it, for example, hapto-2 diphosphine. An hapto-5 cyclopentadienyl ligand has all 5 carbon atoms of the ring bonding to the transition metal center. To note, this is a simple structure when we write M, 1 bond to all pi system. But if we analyze this structure by X-rays, we obtain a figure or a structure where M is bound 1, 2, 3, 4, 5. So we have 5 bonds M to Cp. Eta X value for carbon ligands, where the X value is odd, usually indicate anionic ligand. For example, up to 5, so Cp is anionic. Odd up to 3, Cp is anionic. Odd up to 3, allele, so allele is anionic. Up to 1 odd, allele is anionic. And the number of electron donating by an up to X ligand, where X is odd, is usually X plus 1 ligand. I return to this example. Hapto-5. What is the charge of Cp? Hapto-5 odd, so Cp is minus. What is the number of electron donating by Cp to M? We have X equal 5 because we have 5 carbon atom, and this is anionic ligand. Cp is anionic ligand. So Cp is donor, X plus 1 ligand is donor 5 plus 1 is donor 6 ligands, 6 electrons. If up to X and X is even number, so the ligand is a neutral and donor of X electrons. Consider, for example, hapto-6 C6H6. Hapto-6 even number, so C6H6 is a neutral donor of X electrons, so donor of 6 electrons. Hapto-2 CH2 ethene. This is a ligand neutral because it's hapto-2 and donor of X electron, donor of 2 electrons. Butadiene is a neutral donor of 4 electrons. Cyclooctadiene is a neutral donor of 4 electrons. I will compare the stability of MCP to M benzene. The bond M benzene is weak because this is up to even number. The ligand is a neutral donor of 6 electrons, so M is bound to C6H6 by 6 bonds. But the nature of the bond between this ligand and the metal M is weak. It's formed by the p orbitals of benzene with the d orbitals of M. So M benzene is weak. M Cp is strong because Cp is Cp minus. So when Cp is bound to M, it would not be released. The bond MCp is the most stable bond Ml. But the bond M-benzene is unstable, or M-ethene. To explain the stability of MCp and the instability of M-benzene, we have to draw the structure of cyclopentadienyl and that of benzene. Cyclopentadienyl is C5H5-, where we have minus and two double bond, and we have resonance 4. So the minus is in this atom, or in this, or in this. So the minus is delocalized on the structure of Cp. Consider benzene. Benzene, we have 3 double bond. We have 3 double bond due to the overlap of p orbitals of benzene. So when the metal center is bound to benzene, this is identical to the bonds M3 alkenes. We have 3 ligands alkene: M-alkene, M-alkene, and M-alkene. And we know, and we explained, that the bond M-alkene is not strong. But when metal M is bound to Cp, it's bound from the negative charge minus, which is delocalized in 3 positions. So the bond MCp is strong. The bond MCp is strong due to the nature of the bonds between M and Cp. And the bond of M-benzene is weak because it's identical. Like we say, for example, we have 3 ligand ethene bound to M. This is the difference in the stability. As a conclusion, when you have a bond MCp, M will never release Cp. So we don't have in organometallic chemistry dissociation of Cp ligand. But M-benzene, you may have, for example, dissociation of the benzene ligand easily.